Hello everyone, myself Ishita Sood from MCA first year, and I am going to present a topic on buffer overflow along with Ankit. Ankit is later on going to show the practical implementation of buffer overflow. But before knowing the practical information about it, let's see how and what is exactly buffer overflow is. But before having a knowledge about buffer overflow, let us see a slight topic software vulnerability and what is all in it. So, software vulnerability is basically a defect in software that could allow an attacker to gain control of a system. So, the defects can be like design defects or like poor coding in the system that can be made easy to gain control from the attacker side. So, but exactly the question arises why software vulnerability matters. So, the reason behind it is before having some vulnerabilities or having we know that vulnerabilities can lead to attackers towards our system. So the process basically is like attacker reads the input output ports of the system and he tries to exploit the vulnerabilities through which he can enter the system. So this can lead to like crash of programs, execute arbitrary code, obtain sensitive information, and lead to various compromises of availability, integrity, and confidentiality. So there are some common software vulnerabilities. One is input validation, the other is race condition, the third one is buffer overflow, through which we are going to read a vast topic about it. Format string problems, integer overflow. Now it's our main topic. What is buffer overflow? Let's see. A buffer overflow is basically a condition in where a process attempts to store data beyond the boundaries of a fixed length buffer. Let's see. Let me show you with an example. Here we have like two arrays which are storing like length of 3 and 4 integers or any type of like array variables respectively. And let's suppose here we are filling, it's our second array and we are filling like Aman into it, and now it's all done. And now we are going to fill. Let's suppose we have to store Ankit to this. So it's 5 digit and we are going to store A, N, K. So we are left with like I and T. So in buffer overflow, what basically happens, this is going to be overridden by I and T, like this way. And with respect to A and M, the storage will be done of I and T. So this is basically the condition of buffer overflow. So this will result in extra data overwritten. So in this, basically the problem is if we are going to override the data and it will include some buffers, so it will cause like problems in the further execution of it. So what happens in memory when buffer overflow occurs? So let us see that basically what is happening when a program runs in OS. As we all know, OS is responsible where we have kernel and core processes, and even the temporary processes are running in the operating system. And as you write some code or run a program, the OS will respectively function and the main method of your code will be executed. So, but your actual executable process will be held in memory a specific way and it's consistent between very different processes. So we have a big block of RAM. So RAM can be like two-way, 32-bit or 62-bit, and it's a big system. We don't know like how the big system it is and what all is there. So we use like virtual memory address translation that can lead to like we can say that everything in RAM. So let's see how a RAM basically look like and what all divisions are made in RAM. So the uppermost layer is kernel layer in which the command line parameters are executed and the code processes are executed in it. And the basically division is starting from the bottom layer, text layer, which is the actual code or the program. Then there are like data layer. Data layer is like the division in which uninitialized and initial variables are.
Then we have heap. Heap may have been mentioned from time to time. It's where you allocated large things into the memory. It is a big area that you can allocate huge chunks into and to do various things. Then we have stack. Stack holds the local variable of each of the function. When you call a new function like let's say printf, stack hold that function and then same parameter get put on the end of the stack. We can see that here heap grows in the upward direction and stack grows in the downward direction. As we put data in the RAM, if it is going to the heap, it will go in the upward direction, and when we add memory to the program and it is a stack like so the data will be moved in the downward direction. And stack is the main area on which we can say a lot of buffer overflow occurs. We have some program that actually calling a function. A function is just some area of code that does something and then return back to where it was before. So let's see how a stack area looks like. At the right side of the stack, there is high memory address, and at the left side of the RAM, there is low memory address. Everything which we store in the stack comes to the right side of the stack, which is high memory address, and gets into it. Let's do some allocation of stack memory with a simple C program in Kali Linux. I'm using Kali Linux because it is very easy and helpful software for attacking and hacking and all over there. So I have a program. In this program, I have initialized 500 size of buffer to the memory. So up here we got the main function for C that takes the number of parameters given and a pointer to those variables that you have got. And then we will be held in kernel area of our memory. We have allocated a buffer that's 500 size character long, and then we call a function called string copy, strcpy, which will copy our command line parameter from arguments into our buffer. Our function puts on a return address, and with replacing the code, we need to go back to once we have done string copy. So that's how main knows where to go after it's finished. And then we put on a reference to the base pointer in our previous function. We won't worry about the about too much because it is not too much relevant. So this is just going to be a EBP base. So let's move forward. Let's see how our code runs. So let me open my Kali window. So let's see our program. I have a program on my desktop. So first of all, we will update our Kali terminal with the help of sudo apt get update. My Kali terminal is getting updated. So we will use a GDB in this, which is Linux command line debugger. You are not advised to use this unless you really like seeing lot of assembly and doing really low level Linux things. So let's wait till our Kali terminal is getting updated. So our Kali window has been updated. Now let's see our program. So this is our same program which I have showed you earlier. So let's compile it with GCC -std is equal to C99. This implies user standard C99 to compile the code. Now -g, which means you can see the proper names of the variable. Then -o that writes the build output to our output file. Then I am giving a new name to our program, and then our program from which we have saved it. So I have a spell mistake. Now our program has been compiled, and a function in your stack frames get line number and see the source as you step around in the executable. Now I will open my Linux command line command line debugger. So this is how it gets run. So now I am running a simple code. Let's see that I am writing hello to our program. So we can see that the program is excited normally. That means this hello has been accepted by our program. So from GDB also we can see our program. To see sublines, allocate buffer size, running normally or not, we use this as main. In this we got all the memory of our main that is given by the debugger to that program. So let's see when we overflow our buffer size, like we have 500 buffer size. If we go beyond this, what will happen? So I am using Python with in the C language, because if I am going to write in the C language, it will take a lot of time. I'm using X41, which will write A to all the programs into 506 times. So here we can see segmentation fault. So a segmentation fault is what a CPU will send back to you when you are trying to assess something in memory you should not be doing. You shouldn't be doing. In a nutshell, segmentation fault refers to error due to a process's attempt to access memory region that it shouldn't. When the kernel detects odd memory access behavior, it terminates the process, issuing a segmentation violation signal. Low-level language, including C, usually allow a great deal of flexibility on memory usage and allocation. Thus, they leave many of the memory allocation control aspect to the developer discretion. Now, let's see what causes segmentation fault. The segmentation fault can occur in following conditions. That is violation mapping error. That is SEGV underscore mappers. Assessing memory outside the application address space. Segmentation fault assess error. That is SEGV assessor. Assessing memory where the application had no permission or trying to write on read-only memory space. Error like dereferencing, null, not initializing, or freed pointer variable that reference memory area, buffer or stack overflow can occur after very common programming mistakes. For instance, calling function with incorrect or not initialized pointer as a reference parameter or recursive function with failing stop condition can result in segmentation fault. So let's see how we can prevent a segmentation fault. When programming with pointers, with references and memory arrays, we have to ensure all memory access are within the correct boundaries and that they copy with current access areas. More specifically, we must double check things like dynamic memory allocation, indirect memory access through pointers, array index with value higher than their current allocated size, type consistency through the code and function parameter calling convention, string and buffer operations, points and buffer allocation, stop condition in recursive function. Additionally, these tips are important not only to increase code robustness, but for security also. Moreover, some of those flaws might open our code to attack vectors like malicious code insertion or denial of service exploitation. So, let's go to our program and let's exploit this buffer overflow by removing the segmentation fault within the same. As in our program code, segmentation fault is not actually happened because we overrode somewhere we shouldn't. What happened is that return address was half overwritten with the 41. We can see it with the info registers registers command. So we can see that here. Okay, it is not appearing in this. So if we increase it by more, we will go to more further in overflow. Like if we increase it with 508. So this is also producing a segmentation fault. We are writing 41 here. Now if there was some virus code at 41 41 41, there is a big problem. As when we will execute it, the virus code will get attached with it and it will harm our system. And that's after running this, the return address become 0 into 41 into 41 into 41. So let's see here, it is happened. So this is here 41 that can exploit our system. So it shows that the register, and we can see that the construction pointer is now trying to point 41 41 41 41. So that means that it read this return address value and tries to return to that place in order to code and run it, and of course it can't. So let's remove this segmentation fault. I have a shell code. So this is a shell code which is used to exploit this program. And I will use it to exploit this segmentation fault. And so you can see that I have added x41 with into 360s, and here in this memory address I'm writing the x41s and overwrite it. If I run this code, this program is excited normally. So this is a buffer overflow exploited, and there is no segmentation fault. More beyond the memory size, I have overflowed it, and it is not showing any type of segmentation fault. So this is how buffer flow exploit occurs. So that's all about the buffer overflow exploit. Thank you.